Dear student, warm welcome to NPTEL Phase 2 video course on Geosynthetics Engineering in Theory and Practice. My name is Professor J. N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay, Mumbai, India. This lecture number 42, Module 8, Lecture 42, Geosynthetics for Embankment on Soft Foundation. Now, I focus the recap of previous lecture. That is design of basal reinforced embankment, part is remaining. Then I have covered serviceability limit state, placement of geosynthetics underneath embankment, construction of basal reinforced embankment, widening of existing roadway embankment, and design example partly covered. So, I will now continue with the design example which I have partly earlier covered. Now, step 4, check for sliding failure. Here embankment slides over the reinforcement after formation of crack in the embankment. So, here you can see here is the foundation soil and this is cohesive soil. So, pi is equal to 0. This is the geosynthetic material is placed between the embankment and the foundation soil, and this is the height or the depth of the foundation soil, and this is HE is the height of the embankment. Now, you see that embankment slide over the reinforcement after formation of crack. So, this is sliding on geosynthetics. So, here the basal reinforcement is intact, there is no failure of the reinforcement. What we did the earlier in step 3, and there the embankment slide over the foundation soil. This embankment slide over the foundation soil, and then formation of crack, and there is a rupture of the reinforcement. But it is not this case here. Reinforcement has not been ruptured. Here reinforcement is intact. Only embankment slide over the reinforcement after formation of crack in the embankment. So, two cases are different. So, here we wanted to check what will be the factor of safety against this kind of sliding failure. Here that force diagram is given. Here it is a free field is acting along this direction, and this is the weight of this slide zone Ws. This is the geotextile material. This is H is equal to height of the embankment, and this is the length Ls. That means this is EF Ls. Now, this due to this load there will be a resisting force here. So, this force will be equal to this Ws into tan of delta F plus this is C A into L of S, because this is the length Ls. So, we will see next that what will be the total driving force. So, this force, that is pre-fill, which we have already calculated, that is half into k into gamma h square. So, already we have calculated total driving force pre-fill is equal to 34.36 kilonewton per meter. Now, total resisting force, that is Rg. So, here it will be resisting force Rg. So, this resisting force will be equal to Ws is the weight into tan of delta of E plus Ca into L of S. But here you see Ca is equal to 0 for granular soil, because this embankment, this filling material is granular material. So, this is only pi, there is no Ca. So, this value is 0 because it is a granular soil, not like the other case that foundation soil where pi is 0, but here it is Ca is 0 for granular soil. So, you can write that Ws will be equal to, this is W of S, this equal to, this is the area, this is area triangle. So, this is half into, this is Ls, this is Ls, and this is height He. So, half into Ls into He. So, you can have here Ws, that means half into Ls into He into gamma E, because unit weight of the embankment. So, this will give the, what will be the weight, okay? What will be the weight? So, half area into unit weight of the embankment will give the Ws into tan delta E plus, because Ca is 0 for granular soil. So, you can have total resisting force Rg is equal to this. Okay. Now, you are substituting this value. So, 0.5 gamma E unit weight of embankment is 17, Ls 8.75, and He height of the embankment 3.5, and tan delta E we have considered 80% of tan pi. So, pi value is given 30 degree. So, this will be the 80%, 0.8 into tan of 30 degree. So, this is 0.8 into tan 30 degree. So, this will give that total resisting force Rg is equal to 120.233 kilonewton per meter. Now, you have to check the factor of safety against this sliding. So, this will be equal to Rg divided by P fill. So, you know Rg is 120.233 divided by this driving force P fill is 34.36. So, this will give the factor of safety against sliding is 3.5. So, which is greater than 2. So, it is safe. So, now step 5, check for pull-out strength. So, here you can see this is the foundation soil and this is the basal reinforcement, and due to the pull-out there is a mobilization of the friction between the soil and the basal reinforcement. This is tau, tau at the top and tau at the bottom, and this is the anchorage soil zone, and this is the embankment, and this is the soil slip failure zone. This is the soil slip failure zone. So, you are pulling, that is Tg, you are pulling, and so this is the length which you call the embedment length, or it called the bond length. This is L of S. So, here this is T design will be equal to, this is tau top into this distance LE divided by tau, this is bottom into L of E. So, I can show you better a representation like this. So, you are pulling like this. So, shear stress is acting, this is at the top tau T, because embankment fill material as a phi value, no C value, and this is the foundation material has a C value, but not the pi value. So, there will be the friction between the basal reinforcement and the embankment. This is the embankment. So, this is top, that means this tau top is the mobilization of friction between the embankment and the basal reinforcement, that is tau T. Whereas, in case of the foundation soil, the characteristics of the foundation soil is different. So, there will be the friction or the adhesion between the basal reinforcement and the foundation soil, which is denoted as tau of B. That means shearing stress at the bottom, and this is shearing stress at the tau, because material property for the embankment and the foundation soil is different, and this distance is what you call the L of E. This is the failure surface. So, this is the embedment length of the geosynthetics beyond this slip surface. So, this top will be equal to what will be the vertical force is acting, and what will be the friction between the basal reinforcement and the embankment. So, let us say that is delta of E, because here is a pi. So, there will be the friction between other material, means angle of friction between the basal reinforcement and the embankment is delta of E. So, that is why this will be tan of delta E. So, tau top, that means tau of top will be equal to sigma of V into tan of delta of E. But in case of tau of bottom, that means this is bottom, this will be only Ca, because there is a adhesion between basal reinforcement and the foundation soil, and foundation soil is saturated. This is a cohesive soil. So, this you can have only the Ca. That is why tau bottom will be the Ca and tau top will be the sigma V into tan of delta of E. So, that is why here it is written Tg design will be tau top into L of E, and this is tau bottom into LE, and this is embedment, and this is C equal to 0. Now, you can write, hence Tg design will be sigma V tan delta E, and length is LE, up to that length it is functioning, plus Ca into LE due to the bottom. Again, that this sigma V is equal to gamma E into He, because if unit weight of the embankment field is gamma E and his height of the embankment is He, so this will be gamma E into He, and this tan delta can be written as Ci into tan pi E, where Ci is interaction coefficient and this interaction coefficient value is taken as 0.7. So, this interaction coefficient value also you can find out from the pull-out test. You have to perform the direct shear test and also the pull-out test, and then you can find out the interaction coefficient, that is Ci is 0.7. So, that is why it is written Ci into tan of pi of E. You know that what will be the friction angle of the embankment, and this into L of E plus Ca into Le. Okay, this is for the foundation soil, and this part for the embankment and the basal reinforcement. So, because this Ca we are considering 40% of Cu. We know the unlaid shear strength of the foundation soil is 9. So, Ca can be taken 0.4 into 9, that is 3.6 kilopascal in foundation, because foundation is cohesive soil. Now, for top layer, that is TG design, we have checked or provided the tensile strength of the basal reinforcement at the top is 200 kilonewton per meter. So, you have to check that this is 200 TG design, we can write 200. Gamma E unit weight of the embankment is 17 into Ci, and this Ci interaction coefficient is 0.7. So, you have taken 0.7, and He is height of the embankment 3.5, and then tan of pi E is equal to 30 degree. So, tan 30 degree plus this is Ca into Le. Le is common for both. So, this is C of A is 40% of Cu, that means 3.6, this is 3.6, and then Le. So, this is the Le is common. So, we have to check what will be the value of L of E. So, from this equation you can calculate that Le. So, Le is equal to 7.23 meter. So, for both layer adopt the Le is 7.23 meter. Now, step 6, what will be the required elastic strength of the basal reinforcement or geotextile. Now, you know that E required will be equal to what is T required divided by epsilon F, considering 5% strain, and epsilon F is equal to then 0.05. So, it depends upon that what will be the type of the soil, then accordingly you can select that what will be the strain value. Let us consider for here the geosynthetic strain value we have taken 5%. So, epsilon of F will be equal to 0.05. So, now T design is required tensile strength of geotextile for top layer is we know 200 kilonewton per meter. So, what will be the required elastic modulus of geotextile E required for top layer, that will be the T required is 200 divided by strain epsilon F is equal to 0.05. So, this will give the required elastic modulus of the geotextile about 4000 kilonewton per meter. Similarly, you can also find out the required elastic modulus of geotextile E required for the bottom layer, and we have provided the bottom layer, the Tg value is equal to 100 kilonewton per meter. So, this E required, that means required elastic modulus of geotextile at the bottom layer will be 100 divided by 0.05 will be 2000 kilonewton per meter. So, you know that how to calculate the modulus value for the basal reinforcement for the 2-layer system when it is 200 kilonewton per meter and as well as when it is the 100 kilonewton per meter. Now, step 7, check for lateral squeezing. You can see sometimes there is a possibility of the failure due to lateral squeezing here. So, this is the active pressure which is acting here, and this is the PB, passive pressure is acting, and the shear forces are acting the top, the T up top here, and the bottom is TB, and this is the LS, that is G and H. It is like a block where it is acting. And this is the foundation, the depth of the foundation HF, this is the embankment height is HE, and there is a surcharge load Q of S. So, you know that PA will be equal to half into, this is the foundation soil, half into gamma F into HF square into K of A minus 2 of C of F into HF into K plus Q E1 into HF Ka. So, this is due to the surcharge load. Now, what is Q E1? That is, this is the height of the embankment He, and if gamma E is the unit weight of the embankment, so here it will be gamma E into He plus this surcharge load Qs. So, that is why gamma E into He plus Qs due to surcharge load. So, then Q of E1 is gamma E into He plus Q of S. So, we can write this is 0.5 gamma F HF square, and K you know 1. So, K is 1 minus 2 into CF into HF, again K is equal to 1 plus Q E1 into H of F, because again K is equal to 1. So, we can have PA is equal to this equation. Now, similarly, you can calculate that what is PB. So, PB will be equal to half into gamma of F into HF square into Kp, this is the passive force, plus 2 into C of F into HF into Kp. So, here again Kp is equal to 1. So, you can write that passive force Pb is equal to 0.5 gamma F HF square plus 2 into Cf into HF, because Kp is equal to 1. So, we will use this equation for active force Pa is equal to this equation, and for passive force Pb is equal to this equation. And there are also that Tt and Tb. Okay. So, we are assuming that Qs is equal to 0, that means this part will be the 0. So, we are assuming that Qs is equal to 0. So, then Pa will be 0.5 half, okay. Here gamma F is the unit weight of the foundation soil is 16. So, 0.5 into 16 into this is HF square, that means height of the or depth of the foundation. So, this will be 2.5 square minus 2 into Cf into HF minus 2 into Cf. Cf is foundation cohesion value is 9 into height of the foundation soil or depth of the foundation soil 2.5 meter plus, this is plus QE1 into HF, because QE1 again gamma E into HE into QS, and we are assuming QS is 0, so it will be only gamma E into HE. So you can write here that this is gamma E, unit weight of the embankment 17 and height of the embankment is 3.5, and this is acting for this 2.5. Okay, this will be this into 2.5. So this PA value will be 153.75 kilonewton per meter. Now similarly you can calculate PB. PB is equal to 0.5 here, gamma F is equal to 16 into this is HF square, that is 2.5 square, because this is the height 2.5 of the foundation, 2.5 square, plus 2 into CF into HF. So plus 2 CF is the 9 foundation soil cohesion value into this H of F. So this HF is equal to 2.5. So this is all HF is equal to 2.5. So PB, the passive force will be 95 kilonewton per meter. So we calculated what will be the active force and what will be the passive force. Now you have to calculate that what will be the shear force, that means shear is acting at the top, that means EF portion, and also shear force which is acting at the bottom, that is G of H. So shear force at the top of the foundation block, that is EF portion, that is TT, is designated as TT. So TT will be equal to CA plus sigma VT, because for top vertical force into tan delta F. Okay, because for tan delta F in the foundation soil this is 0. So we can write the equation TT will be CA into LS. That is why TT is equal to CA into LS. Now this CA value you are carrying 40% of the C value, unlaid shear strength of the foundation soil. So that is why 40% means 0.4 into 9 into LS. LS we calculated earlier, that is 8.75. So this will give you that shear force at the top of the foundation block, that is TT is 31.5 kilonewton per meter. Here TT at the top is 31.5 kilonewton per meter. Now that shear force at the bottom of the foundation block in EF portion TB, that means here what it will be. So here again that CF plus sigma VB, that means this is the vertical force due at the bottom into tan pi F into L of S, because this portion is equal to the 0, because this foundation soil what there is only that C of F but not the pi F. So you can write CF into LS, and you know CF value is equal to unlaid shear strength of foundation soil is 9 into LS is 8.75. So this will give you 78.75 kilonewton per meter for TB. Now you have to determine that factor of safety against the squeezing. So factor of safety against squeezing will be equal to PB plus TT plus TB divided by P of A. So, you can have from here. This is PA and this is PB plus this is TT and this is TB, all are acting in this direction. Okay. So, PB plus TT plus TB will be equal to P of A. Okay. So, you can write that factor of safety against squeezing is PB plus TT plus TB divided by P of A. So, PB we have calculated, that is 95, TT we have calculated, this is PB, we have calculated 95, and also we have calculated TT 31.5, this is 31.5, and also at the bottom here TB we calculated 78.75, this is 78.75. This divided by P of A, P of A 153.75. Here we have calculated P of A 153.75. So, that is why 153.75. So, you are substituting this all the value of PB, TT, TB and PA, and then you calculate what will be the factor of safety against squeezing, and this we found 1.335, which is greater than 1.3, that means it is the safe. So, we checked against the squeezing and this is on the safer side. Step 8, check for drainage and filtration. And whenever you will design this embankment on the soft soil, or whenever you are introducing this basal reinforcement in between the foundation and embankment soil, you should check the drainage and filtration. This is very important. So, you require gain side distribution of the subgrade soil. You have to calculate one retention criteria, that means what will be the maximum apparent opening size of the geotextile material. 2, permeability criteria, that means coefficient of permeability of the geotextile should be greater than coefficient of permeability of the soil. It is always, and if coefficient of permeability vary depending upon the code or the specification you use. As per STM, this coefficient of permeability of the geotextile should be 10 times the coefficient of permeability of the soil. As per UK, the coefficient of permeability of the geotextile should be greater than equal to 5 times of coefficient of permeability of the soil. And number 3, clogging criteria. That means what should be the minimum apparent opening size of the geotextile, that means O95 or equivalent opening size of the geotextile. So, these are the 3 criteria must satisfy. Step 9, check the settlement and the construction sequence. You can check the settlement as per the conventional geotechnical engineering problem. You can use any basic soil mechanics book and can check that what will be the settlement, and also you should check the construction technique. Step 10, required properties of geosynthetics. So, ultimate tensile strength of the geotextile in the machine direction, it should be greater than equal to 200 kilonewton per meter, the top layer. So, what we mention that you need, because it is a very high strength of the basal reinforcement, it is about 300 kilonewton per meter. So, we have divided into the 2 layer of the basal reinforcement, and the top layer, the strength, ultimate strength of the geotextile in machine direction is 200 kilonewton per meter, and at the bottom layer this ultimate tensile strength of geotextile in the machine direction should be greater than or equal to 100 kilonewton per meter. Also spacing between these two basal reinforcement is kept about 200 millimeter. Now ultimate tensile strength of the geotextile in the cross machine direction should be greater than or equal to 60 kilonewton per meter for both the layer. So here it is required to check that what will be the ultimate tensile strength in the machine direction, what will be the ultimate tensile strength in the cross machine direction, because in the cross machine direction also plays also very important role in case for the design of embankment using the basal reinforcement. And then accordingly you have to select the basal reinforcement from the manufacturer side. So sometimes you avoid that the strength in the cross machine direction, but you must check. And embankment design is quite confusing, so you have to be very careful for the design of embankment using geosynthetic material on soft foundation. And seam strength of the geotextile should be greater than or equal to 60 kilonewton per meter for both layers. And you require also the limit strain, and the limit strain is equal to 5%. So this is the way you can design, and then we are mentioning here the summary of the required geotextile, that property. Ultimately you have to give this property, that you know that ultimate tensile strength of geotextile in machine direction greater than or equal to 200 kilonewton per meter top layer, ultimate tensile strength of geotextile in the machine direction is greater than or equal to 100 kilonewton per meter bottom layer, ultimate tensile strength of geotextile in the cross machine direction greater than or equal to 60 kilonewton per meter for both layer, seam strength of geotextile greater than or equal to 60 kilonewton per meter for both layer, and limit strain is 5%. So this is the required geotextile property. Now we are giving another example. Determine the minimum height of a low embankment, that is unpaved roadway, without and with geotextile, to prevent the foundation failure due to the wheel load. Also compare the result, and you can use the following given detail. So here cohesion of the subgrade soil is 10 kilopascal, axial load 102 kilonewton, little bit higher than the standard. So wheel load will be the half of the axial load, that means 102 divided by 2 is about 51 kilonewton. Allowable tire pressure P is 500 kilopascal, and dart depth is 5 centimeter, and number of passes is 1000. We have also described earlier how you have to design the unpaved road by the given by the Giroud and the Norway, and also yes, Army crops, then other different method. Here in this example, this is the geotextile base layer beneath the road embankment, and this is small h is the height of the embankment, and this is single axial load. No, this is 51 kilonewton, this is 51 kilonewton, this is single axial load, and this is the embankment, and this is the geosynthetic is placed between the embankment and the foundation soil. Step 1 given data, axial load is equal to 102 kilonewton, allowable tar pressure P is equal to 500 kilopascal, rod depth is equal to 50 millimeter, and CU, undense shear strength of the soil, is 10 kilopascal. And value of NC for different rod depth is given by Stewart ETL 1977. They have performed the extensive field test with and without geosynthetic material, and they have obtained this chart. The NC value is equal to 3.3 with no geotextile. NC value is equal to 5 with geotextile. NC value is equal to 2.8 with no geotextile. NC value is equal to 6 with geotextile. So here, when number of passage is 100 and rod depth is greater than 100 millimeter. When NC value is 5, number of passage is equal to 1000 and rod depth should be less than equal to 50 millimeter. NC when 2.8, number of passage equal to 1000 and rod depth is less than equal to 50 millimeter. Here NC is equal to 6 with geotextile, number of passage is equal to 100 and rod depth greater than equal to 100 millimeter. We will check in our example what it lies. Now, the vertical stress sigma h at a depth h is given by Business 1883 for a loaded circular area. So, you can calculate the what will be the vertical stress due to the circular loaded area. So, this angle is equal to theta, this is also theta, this is the P and this is the B dash and this is height h. So, we know this equation from Business that sigma h is equal to P into 1 minus 1 divided by 1 plus R by h whole square whole to the power 3 by 2. So, what P is equal to allowable tar pressure is 500 kilopascal and R is equal to radial horizontal distance, and here the axial load is 102 kilonewton and single wheel load W will be equal to 102 divided by 2, that means 51 kilonewton. We know the equation R is equal to W divided by pi into P whole to the power half. So, this W is equal to single wheel load is 51 kilonewton. So, this is 51 kilonewton. This divided by pi into P and P is allowable tar pressure, that is 500 kilopascal whole to the power half. So, you can calculate the R value. So, R value is 0.18 meter. So, we know what is R value here 0.18 meter. Okay. Now, step 2, calculation of the depth of the embankment HU, we designated as a HU without geotextile. So, for the rod depth of 50 millimeter and number of passages 1000. So, we can make use of the Stewart chart, that is Stewart given by 1988 in 1977. So, NC value is 2.8 without geotextile. You can see from this chart. Okay, here, because number of passages is 1000 and rod depth less than equal to 50 millimeter. So NC value will be 2.8 with no geotextile. So we will take this column. So then you can see here that NC value is 2.8 without geotextile, because rod depth is 50 millimeter, number of passages is 1000. Now sigma HU, which is the bearing capacity of the foundation soil without geotextile. Okay, we are considering bearing capacity of that equal to NC into CU. So NC without geotextile from the chart we obtain 2.8 into CU. CU is the undrained shear strength of the soil. That means that is 10, which is given. So 2.8 into 10 is 28 kilopascal. So we obtain that sigma HU, that means bearing capacity of the foundation soil without geosynthetics is 28 kilopascal. And we have considered that height or thickness of the embankment without geotextile is HU. So now substitute the value in the Bougenis equation. So we know sigma h is equal to P to 1 minus 1 by 1 plus R by H whole square whole to the power 3 by 2. Now here undrained force case, that sigma h, that means sigma HU. So sigma HU mean this is 28 undrained force case. So this is 28 and P you know 500. So P already we know that P value we have calculated, that is 500. So this is 500 into 1 minus 1 upon 1 plus R we calculated is 0.18. R just we calculated here, R value calculated 0.18 meter. So this is 0.18 meter divided by HU. That HU is the thickness of the pavement without geosynthetic material. So you can see that all values are known except HU. So from this equation you can solve and find out what should be the thickness of the pavement without geosynthetic, that is HU is equal to 0.91 meter or is equal to 91 centimeter. Okay, this is the thickness of the pavement without geosynthetic material. Now step 3, calculation of the depth of the embankment with geotextile, which is designated at HR. So again for rod depth 50 millimeter, number of passages 1000 from Stewart ETL chart 1977, NC value will be 5 with geotextile. You remember rod depth 50 and 1000 passes. So NC value will be the 5. So you can use this design chart. Okay. Number of passage is 1000, NC value 5 with geotextile, rod depth is 50 millimeter. So in this column, so we are telling NC value is equal to 5. So here NC 5 with geotextile. So sigma HR, that means bearing capacity of the foundation soil with geotextile, will be equal to NC into CU. So NC value with geotextile 5 into CU value is 10. So 5 into 10 is equal to 50 kilopascal. So bearing capacity of the foundation soil with geotextile is 50 kilopascal. Now we are assuming HR is equal to thickness of embankment with geotextile. Now you are substituting the value by Bougenis equation. This is the equation. So here the sigma H value mean bearing capacity sigma HR in case of reinforcement 50 kilopascal. So, this is 50 kilopascal, P is 500, 1 minus 1 plus R is 0.18 and this is HR, the thickness of the pavement with geotextile, the whole square whole to the power 3 by 2. So, now if you can solve this equation, so you can obtain the thickness of the pavement with geotextile is 0.667 meter or 66.7 centimeter. So, you see that with geotextile you are having 66.7 centimeter, whereas without geotextile you are getting 91 centimeter. So, we have to check what should be the saving in the embankment thickness in terms of the percentage. So, with the use of geotextile, saving in thickness, that is 91 centimeter minus 66.7 centimeter, that means 24.3 centimeter. So, percentage of saving will be 24.3 divided by 91 into 100, about 26.7 percentage. So, you can see that with the introduction of the geosynthetic material and how you can reduce the thickness drastically. So, this amount of the good quality aggregate also can be the saved. So, in this part I showed you that what are the design for the embankment using the basal reinforcement, and then also that for the road construction for the embankment, that if we can use the Business equation and you can also use that Stewart chart, and depending upon the rod depth and the number of the passes and the axial load. So, you can also calculate it what will be the thickness of the pavement without and with geosynthetic material, and you can also check that what percentage of the saving. But you require proper kind of the geosynthetic material selection. So, these are the part which we have covered for the embankment using the geosynthetic material. Please let us hear from you any question. Thanks for listening.